All right, folks, so we're going to go through the workflow of what might be a typical make a buffer problem that you might find on the exam. And before I do that, I wanted to introduce you to a molecule that I, as a biochemist, use quite often, and that is a molecule which is simply referred to as tris. Now, tris is an amine, which means it's a nitrogen with a lone pair. And it's not ammonia, in which case you'd have three hydrogens around it. Instead of three hydrogens, you have three hydroxy methyl groups. So HO, and then this elbow of this structure here is actually CH2, CH2, CH2. Okay, so we have that lone pair there, which means it can act as a base, and when it is protonated, the conjugate acid will have picked up a proton and be a cation there. And so the reason why, even though the molecule itself is a base, we sort of define this by its conjugate acid, because we really care about with these things, because we tend to define things based on a pH scale, not a pOH scale, is the pK value of the conjugate acid is 8.1. And so this is a molecule that's very common in a biochemistry lab. Biochemists use it all the time. And the reason why is because with this pK value of 8.1, we can easily make buffers, in the 7.5 to 8 range, which easily constitutes what a lot of what you'd find inside of cells and where biomolecules are happy. So the question, or the problem we're going to try to solve here, is to make a, say, 200 millimolar buffer with 1.0 molar tris base and 1.0 molar hydrochloric acid, and then we want to make it 1 liter at pH, say, 7.5. All right, so that's what we're going to try to do. And so before we go much further, let's take a look at what the equilibrium that's relevant to tris is. And so whereas normally we're doing HA dissociates into H plus and A minus, in this case, our HA species is actually the conjugate base of A, which is a weak base. But this is still how we're going to define it. And again, the pKa is 8.1. And so before we get started, let's just make sure we have all the right information and that everything makes sense. So, the first thing you need to ask, and I promise I wouldn't ask you a question where the answer to this question is no, but you want to make sure that the starting pH, or your target pH, I should say, is within 1 pH unit of your pK, and in fact they are. All right, so the other pieces of information we need are the total concentration of our buffer, and we also need to know the volume that we're making, just so we know how much of our stock solutions to add, and then the two stock solutions that I'll do in a different color are tris base and hydrochloric acid. So in other words, what we're adding directly, this right here, is tris base, and then hydrochloric acid, what that will do is protonate our tris base to give us the HA species. And all of this has to do with the Henderson-Hasselbalch equation, pH equals pKa plus log of A over HA. And again, in class, we've typically done A minus over HA. But in this case, not that it really matters because the workflow is identical. It's A over HA plus. All right, and so just before we get to the end here, what we're going to eventually solve for is at equilibrium, an equilibrium defined as an amount of A and HA that give us pH 7.5. Okay, we're going to have a certain amount of A and a certain amount of HA given our target pH and our pK value, and we're going to make it with these two stock solutions, tris base and HCl. And so basically, if we just think about how this is going to happen, HCl does not have any A in it, right? So that's just a strong acid. So in other words, the amount of A plus HA that we need all have to come from tris base. And then the amount of HA that we have is going to be a fraction of that that's converted to the HA species by the addition of hydrochloric acid. All right, so let's just work through that. Hopefully it makes more sense as we go. So the first thing we want to do is start out by doing the math of the Henderson-Hasselbalch equation. So our target pH is 7.5, and that's going to equal the pK value, which is 8.1, and then the log of the A and the HA, which at this point we don't yet know. So if we subtract 8.1 from each side, we'll get negative 0.6 equals log of A over HA, and we get rid of that log by taking each side as the exponent of 10, so 10 to the negative 0.6 equals A over HA, and then we can plug 10 to the negative 0.6 into our calculator and get our answer, which I've already done here. You can see that below the number here, 10 to the minus 0.6, and that's 0.2512. So equals 0.2512. And those digits are not significant. And so, again, just a good opportunity to stop and make sure this makes sense. First of all, our A to HA ratio, in order to make a buffer, has to be between 0.1 and 10. And if not, it either won't work, or perhaps more likely, you've calculated something wrong. We know it should be between 0.1 and 10 because we've already determined that our target pH and our pK value are in the acceptable 1 pH unit range, which is, if you look at the Henderson-Hasselbalch equation, the definition of a 0.1 to 1 ratio. And so when we go through the math, we see that indeed this ratio is larger than 0.1 and less than 10. Okay? So let's take that to another page, 0.2512. A to HA equals 0.2512. Oh, it also makes sense to make sure the magnitude of this number, as far as whether it's greater or less than 1, matches up with the relationship between pK and pH. So we're looking for a pH of 7.5, which is lower beneath our pK value of 8.1. So it's on the acidic side, which means that with respect to our A to HA ratio, that number better be less than 1 because our HA is going to have to be in greater fraction than our A, and it is. It's less than 1, so that's all good. All right, so back to the math here. Our A to HA ratio is 0.2512, and we also know that our A plus HA is 200 millimolar. Now again, I tried to make a big deal of this in class, of where folks are going to get this wrong. By saying I've got a 200 millimolar tris buffer, that's not 200 millimolar tris, it is 200 millimolar tris, which is A, plus tris H+. So it's both protonated and deprotonated species together is my analytical concentration. All right, now because we're doing this at 1 liter and because we're expressing our A to HA ratio in moles, I think it makes more sense to me. It makes the math much easier if instead of working in concentrations, we work in the number of moles. So I would advocate to rewrite this. A plus HA is 0.200 moles. And we can do that because the volume is the same for both A and HA over in this ratio. So now we have 2 equations and 2 unknowns, and we can solve them for each other. So if you multiply this one, both sides of the equation, by HA, you get A equals 0.2512 HA, which can then be plugged in over here. 0.2512 HA plus HA equals 0.200 moles. And then you add these together, 1.2512 HA equals 0.200 moles. And then we can solve for HA by dividing both sides by 1.2512 and take that to the calculator. So that means we're adding 1 to this, taking the inverse and multiplying it by 0.2 moles, and we'll get HA equals 0.160. 0.160. Now going back to, we have 2 different equations we could plug this into to solve for A. And to me, it's sort of very easy to do this one in your head. If HA is 0.16 and the sum is 0.2, then A clearly has to be 0.04 moles, right? Because you add those together and you get 0.2. So now we have the amount of A and we have the amount of HA. So going back to our math, which is starting to get sloppy, we see that, I'll do this in a new color, our two solutions are 1 molar tris base and 1 molar HCl. Okay, so again, both A and HA have to come from tris base. There is no tris in hydrochloric acid. That just changes the protonation state. So even though we figured out how much A and HA we have, the amount of tris that we need has to be the total number of moles represented, which means we need 0.2 moles divided by 1 liter total solution, okay, which means, 1 mole per liter concentration. Let me erase that, do it neater. So divided by 1 mole per liter is going to give us a volume in tris, which is going to be 0.200 liters of 1.0 molar tris. So that's the first thing we need, and then all we need to figure out is how much hydrochloric acid that we need. So according to these numbers that we figured out, of those 200 millimoles or 0.2 moles of tris that we need to add, 0.16 of them are protonated. So that 0.16, the only way we turn our 200 millimoles of tris into the protonated tris are to add this number of moles of hydrochloric acid. Okay, so now it's the same thing, M1V1, M2, V2. If we need our final concentration to be 0.160 moles of H plus, divide that by 1.0 molar solution, we're going to get 100, so 0.160 liters of 1.0 molar HCl. All right, so that is the second half of our recipe. So we've added that volume of tris, this volume of hydrochloric acid, and what that's going to do, if we just go back to what our equation is, HA going to H plus and A, we put in 100% of our A species, and then we protonated a certain fraction with hydrochloric acid. And so then all we need to do is bring it up to volume. So if I've got, that's a 0 there, 200 milliliters of tris and 160 milliliters of hydrochloric acid, that's 360 total, which means I need 640 plus 640 milliliters of water. All right, so hopefully you can rewind this and watch it again until you understand, but just to sort of recap what's going on here. We made a buffer of a certain concentration at a certain volume with a certain target pH, and I gave you some solutions that you could use to make it. Any buffer situation could be described by an equilibrium between the protonated and deprotonated species, so both members of that conjugate pair. You plug that into the Henderson-Hasselbalch equation with your target pH and your established pK to solve for your A to HA ratio, so that's just math. And when you have that A to HA ratio, you always have a second equation, which is the sum of the protonated and deprotonated version, which would be given to you in the problem. And you can solve those equations for each other and therefore get, let's do purple, at the end of the day, your amounts of HA and A at equilibrium, right? And so how do you figure out how much of those you need? Well, again, there's a couple different ways we could ask you. We could give you the HA and the A species as stock solutions. So you could have, say, acetic acid and sodium acetate. In this case, I could have given you tris base and tris HCl, which would have been the protonated version of it, and then you would just add these molar quantities from your stock solutions. But in this case, I'm giving you just one molecule, the A molecule, and you can tell that from the way the problem was worded. You're given tris base, which you know if that's the base, it has to be that member of the conjugate pair, and hydrochloric acid, which isn't HA or A, but it's a way to turn A into HA. So you have the appropriate molar quantity, and therefore all of your tris comes from tris itself, and then a certain amount of it is protonated. All right, good luck.